Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on complex analysis, lecture number 9, in which we will discuss about the analytic function and Cauchy-Riemann equation. Now we define the differentiability of a function of a complex variable. Let W equal to function of Z in a domain D. Then Fz is said to be differentiable at Z equal to A if the increment ratio delta W by delta Z equal to function of A plus delta Z minus function of A by delta Z tends to unique limit as delta Z tends to 0. That is, Z tends to A. If delta Z tends to 0, then if this is, let Z equal to A plus delta Z, and for delta Z tends to 0, we get this 0 tends to 0, that means Z tends to A. Z tends to A along any path of the domain D. This unique limit is called the derivative of Fz at Z equal to A and is denoted by F dash A. We write F dash A equal to limit delta Z tends to 0 F A plus delta Z minus F A by delta Z. Now we shall prove a theorem. Differentiability implies continuity but not conversely. Prove. Let Fz be a function of Z. Let W, here W, delta W by delta Z limit delta Z tends to 0 equal to F dash Z. At Z equal to A, we write F dash A, and F dash A equal to F A plus delta Z minus F A by delta Z limit delta Z tends to 0. Given that differentiability exists, let F dash A exist. We shall have to show that Fz is continuous at Z equal to A. This to show. Now F A plus delta Z minus F A equal to delta Z F A plus delta Z minus F A by delta Z, taking limit delta Z tends to 0 F A plus delta Z minus F A equal to limit delta z tends to 0, delta z, again here we may take limit, delta z tends to 0, f a plus delta z minus f a by delta z implies that limit delta z tends to 0, f a plus delta z minus f a equal to limit delta z tends to 0, this is f dash a, f dash a, this is equal to delta z equal to 0, putting f dash a equal to 0 implies that limit delta z tends to 0, f a plus delta z equal to f a, that is when we take, if we take a plus delta z equal to z, then limit delta z tends to 0, z equal to limit delta z tends to 0, a plus delta z, that is z tends to a, this is number 1, this is number 2. Therefore, using these two in one, we get limit z tends to a, fz equal to fa. Therefore, fz is continuous at z equal to a. Therefore, here we see that if derivative exists, f dash a exists, then fz is continuous, means limiting value of fz for z tends to a equal to functional value of fz at z equal to a, that is fz is continuous. So here we get differentiability implies continuity. Now we shall show that converse is not true. Conversely, we shall show that fz is continuous but not differentiable. For this we shall take help of an example, as we know that if any concept is false in any particular case, then it is said that the concept is false. Here we take the example fz equal to modulus of z square. Since modulus of z square equal to x square plus y square, therefore fz equal to x square plus y square, which is polynomial in variables x and y. Therefore, fz is continuous everywhere. Now we shall show that it is not differentiable at the origin. Now f dash a equal to limit delta z tends to 0, f a plus delta z minus f a by delta z. Since fz equal to mod z square, Therefore this equal to limit delta z tends to 0 a plus delta z mod square minus mod a square by delta z. This equal to limit delta z tends to 0 a plus delta z and a plus delta z bar. Since we know that mod z square equal to z bar. Minus a bar by delta z. Equal to limit delta z tends to 0 a plus delta z a bar plus delta z bar minus a bar by delta z equal to limit delta z tends to 0 a bar plus a delta z bar plus a bar delta z plus delta z bar minus a bar by delta z. Here a bar cancel, so only remains other terms. Limit delta z tends to 0 a delta z bar plus a bar delta z plus delta z bar by delta z equal to limit delta z tends to 0 a delta z bar by delta z plus a bar delta z by delta z plus delta z bar by delta z equal to limit delta z tends to 0 a delta z bar by delta z plus a bar plus delta z bar. Let this is number 1. Since we have taken delta z tends to 0 implies that delta x plus I delta y, delta z equal to, since z equal to x plus I y, so if we use delta z, then here delta x, here delta y tends to 0 implies that delta x tends to 0 and delta y tends to 0 implies that delta x minus I delta y tends to 0 implies that this is delta z bar tends to 0. So here we see that f dash z equal to this quantity. So using limit individual terms implies therefore f dash a equal to limit delta z tends to 0 a delta z bar by delta z plus a bar plus this is 0. This equal to a bar plus a limit delta z tends to 0, delta z bar by delta z. Let this is number 2. Here let we take delta z equal to rho cos theta plus I sin theta equal to rho e to the power I theta. Therefore, delta z bar equal to rho cos theta minus I sin theta equal to rho e to the power minus I theta. Therefore, delta z bar by delta z equal to rho e to the power minus I theta by rho e to the power I theta equal to rho cancel e to the power minus 2 I theta. This is number 3. Now let a equal to 0 into we get f dash a equal to a equal to 0, then a bar will be also 0. Since a is a complex number, 0 plus 0 limit delta z tends to 0, delta z bar by delta z equal to 0. That is f dash 0 equal to 0. This is number 4. Putting the value of theory, into, we get f dash a equal to a bar plus a e to the power minus 2 I theta taking a tends to 0, we get limit a tends to 0 f dash a equal to limit a tends to 0 a bar plus a into cos 2 theta minus I sin 2 theta. Since theta may be changed, so the value of f dash a at limit a tends to 0 does not tends to unique limit. That is, limit a tends to 0 f dash a not equal to 0 f dash 0. Therefore, f dash a does not exist. Therefore, f dash a limit a tends to 0 not equal to a unique quantity. Therefore, f z is not differentiable at a equal to 0, that is, it is not differentiable at the origin. Now we define analytic function. A function which is defined and differentiable at each point of a domain D is said to be analytic in that domain. Means the function is differentiable at each point of the given domain. Then the function is called analytic. We shall have to remember that we have to examine that at each point of the domain the function is differentiable or not. If it is not differentiable at any particular points, then it is not analytic. The second name of analytic function is called regular function. Now we describe about the Cauchy-Riemann equation for fz function of z to be analytic. Statement for necessary condition. If a function fz, that is function of z, equal to uxy, u is the function of xy, and plus ivxy is differentiable at any point z equal to x plus iy, then four partial derivatives ux equal to del u by del x partial derivative, vx equal to del v by del x partial derivative of v with respect to x, similarly uy and vy should exist and satisfy the equation ux equal to vy and uy equal to minus vx. This is the statement for the necessary condition of Cauchy-Riemann equation for fz to be analytic. Now we shall prove this. Since fz equal to uxy plus ivxy is differentiable at a point z, if it is differentiable, then the ratio fz plus delta z minus fz by delta z must tends to unique limit as delta z tends to 0 in any manner. Since in the real case we know that the increment of the variable is along a straight line, that is along the real line, but for the case of complex number we may take the delta z tends to 0 along in any manner, that is in argand plane in any direction. Since z equal to x plus iy, therefore delta z equal to delta x plus I delta y, and function of z plus delta z, increment in z, then increment in x and increment of y we will get. Therefore that equal to u x plus delta x, y plus delta y, plus I v x plus delta x, y plus delta y. Now fz plus delta z minus fz by delta z equal to value of fz plus delta z is this, minus fz equal to uxy plus I vxy, delta z equal to delta x plus I delta y. Now we separate u and v and then dividing by delta x plus I delta y. Let this is number 1. Now let delta z tends to 0, as we have stated that delta z tends to 0 in any manner, in any direction. Let the increment is along x direction. Let delta z tends to 0 be taken in any manner. Now we take the increment of z along x axis. Therefore, delta y equal to 0. Then limit delta z tends to 0, f z plus delta z minus f z by delta z equal to limit delta x tends to 0. Here delta y is 0. So we write u x plus delta x y plus I v here a minus, here minus u x y by delta x plus I v x plus delta x y minus v x y by delta x, and this is f dash z equal to, this is the variation in x, change in x. So we may write this del u by del x plus I, here also we see that y remains same, only change in x, I del v by del x, that is ux plus I vx. This is number 2. Since we may take delta z tends to 0 in any manner, now we take the increment of z along y axis, that is there is no increment along x axis, that is delta x equal to 0. Now limit delta z tends to 0, fz plus delta z minus fz by delta z equal to limit delta y tends to 0. Here we take delta x 0, so u x y plus delta y minus u x y. Here delta x equal to 0, so remains only I delta y plus I, limit delta y tends to 0. Here delta x is 0, so v x y plus delta y minus v x y. Here delta x is 0, so remains I delta y. Here 1 by I, since change in y, so this is del u by del y, 1 by I plus here I cancel. So this is del v by del y. We write minus I square for 1 and I del u by del y plus del v by del y. This is equal to minus I uy plus vy. This is equal to vy minus I uy. From 2 we have f dash z equal to ux plus I vx. So since f dash z gives unique limit, that is the value of the limiting value of f dash z will be same. So right side of equation 2 and 3 be same. Therefore ux plus I vx equal to vy minus I uy implies that ux equal to vy and vx uy equal to minus vx. Proved. Now we shall describe about the statement for the sufficient condition of Cauchy-Riemann equation. The continuous one valued function fz is analytic in a domain D. Number 1, if the four partial derivatives ux, vx, uy, vy exist and are continuous. Number 2, satisfy the Cauchy-Riemann equations at each point of the domain D. We have to show that the function fz is analytic in domain D under these two conditions. Now proof. Let w equal to function of z, and function of z is written as uxy, u is the function of xy plus I, v is the function of xy. Number 1 implies that delta w equal to delta u plus I delta v. Since given that u x y is continuous and differentiable in the domain D, ux, vx, uy, vy exist, that means firstly you have to be continuous, then differentiable. For differentiable of a function, the function must be continuous. So ux y is continuous and differentiable given in the domain D. Therefore, by means of mean value theorem for the function of two variables, we shall find the value of delta u. Since delta u equal to u function of x plus delta x, y plus delta y minus uxy. Here we subtract ux plus delta xy and also add this in the next line. This term and this term remains same. By mean value theorem, we get here, we see that x plus delta x here also x plus delta x, same. But here we see that y plus delta y, here y. So y is changed. So we may write this delta y, partial derivative of u with respect to y, uy, that is x plus delta x, same. Here we write y plus theta into delta y, where theta lies between 0 and 1. Now this part, this here we see that x plus delta x and here x. So value of x is changed, y remains same. So by mean value theorem, we write this delta x, partial derivative of u with respect to x, ux. Here x is changed, so x plus theta dash delta x and y same. Theta dash lies between 0 and 1. 0 theta dash 1. And delta x less than delta and mod of delta y less than delta. Now, since uy and ux are continuous, so for the property of continuous, uy here, uy x plus delta x, y plus theta delta y minus uy xy. Here value of x is changed and value of y is also changed. Less than epsilon, as uy is continuous. Taking modulus of delta x less than delta and modulus of delta y less than delta. Now we take this value of this quantity under modulus is alpha, let, where modulus of alpha less than epsilon. Therefore, we may write uy x plus delta x, y plus theta delta y equal to uy xy plus alpha. This is number 4. Similarly, ux is continuous, and similar to this equation 4, we may write ux x plus theta dash delta x equal to ux function of xy plus beta, where modulus of beta less than epsilon. Using 4 and 5 in equation 3, we get delta u equal to uy. Here uy x plus delta x, y plus theta delta y equal to uy x plus y, ax comma y plus alpha. So we write here, in place of this, uy xy plus alpha into delta y, and here plus delta x, here delta x, and ux x plus theta dash delta xy equal to ux partial derivative of u with respect to x function of xy plus beta into delta x. This is equation 6. Similarly, delta v equal to vy xy plus alpha dash. In place of alpha, we take here alpha dash. Here, similar, u, in place of u, we write v, and we get this equation 7, where modulus of alpha dash less than epsilon dash and modulus of beta dash less than epsilon dash. Now, delta w by delta z equal to, delta w is delta u plus I delta v, and delta z equal to delta x plus I delta y. Now we put the value of delta u from 6. Here uy into delta y, no necessary to write function of xy, uy delta y plus alpha delta y. Similarly here ux delta x plus beta delta x. Similarly I delta v, vy delta y plus alpha dash delta y. Here vx delta x, beta dash delta x, and by delta x plus I delta y. Since uy, partial derivative of u with respect to y, uy equal to minus vx, and we write ux delta x here, I vy, ux equal to vy, here ux equal to vy, we write here, since uy equal to minus vx and vy ux equal to vy. In place of vy, we write ux, I ux delta y. Here I vx delta x. Next we write alpha delta y plus beta delta x plus I alpha dash delta y plus I beta dash delta x by delta x plus I delta y. Here we write ux, here ux common, and here ux delta x common from these two terms, delta x, here ux plus I vx. Here minus vx written, minus vx delta y, for minus 1 we write I square vx delta y. So we take common here delta y, here I delta y, we take common. Here remains ux, and here I square means I vx. and remaining terms are same. Alpha delta y plus beta delta x plus I alpha dash delta y plus I beta dash delta x by delta x plus I delta y. Here we see that common ux plus I vx, so remains delta x plus I delta y by delta x plus I delta y. Here we take alpha, here delta y, common delta y, alpha plus I alpha dash delta y by delta x plus I delta y. Here we take common delta x from these two terms, beta plus I beta dash delta x by delta x plus I delta y. Here only remains ux plus I vx, this term cancel. So we take left side, delta w by delta z minus ux plus I vx, and take modulus both sides. So we get here modulus of alpha plus I alpha dash and modulus of delta y by delta x plus I delta y. Similarly, modulus of beta plus I beta dash, modulus of delta x plus by delta x plus I delta y. Since here modulus of delta y less than equal to modulus of modulus of delta x plus I delta y, so this is less than 1. So if we replace this side will be greater. So modulus of alpha plus modulus of alpha dash, modulus of I equal to 1 plus modulus of beta, modulus of I equal to 1 and modulus of beta dash. Since modulus of alpha less than epsilon, modulus of alpha dash less than epsilon dash, modulus of beta less than epsilon, modulus of beta dash less than epsilon dash. So right side is 2 epsilon plus 2 epsilon dash. Taking delta z tends to 0, here we get this is less than very small quantity. So we get limit delta z tends to 0, delta w by delta z equal to ux plus I vx according to the case we have already, limiting case we have seen earlier. So this is equal to f dash z equal to ux plus I vx. Since ux is the partial derivative of u with respect to x and which is unique quantity, and vx is also unique limit, unique quantity. So this becomes unique limit, that is f dash z is differentiable in domain D, therefore fz is analytic. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.